And so that's where we're looking for the invariant of what can we say about regular languages. And so that invariant is going to come from some structural limitations of this machine model. So in these DFA, which we know are exactly as strong as NFA or as regular expressions, so we're just going to focus on this model as the one that's easiest to analyze. So in a DFA, all we know about the string that we've read so far is encoded in our state. So all the memory that we have is represented by the states that we're in. So that means that automata can only remember finitely much information about the string that we've read. So it can only remember finitely far in the past. If we've been reading a string, one symbol at a time for a really, really long time, we're going to start forgetting stuff about the beginning of the string because we won't have enough state, enough memory to remember everything it is that we've read so far. So if a computation path in the machine visits a state in the machine more than once, basically what that machine has done is forgotten everything there was to know about what we saw in the string along that loop that brought us back to the same state. So the machine can't tell the difference between the first time it visits a state and any future, bless you, times that it comes to it. And so this is the invariant property that we want to encode that's going to have to be reflected in the sets of strings that are accepted by DFAs. So formally, here's what that property looks like. And it takes a little bit of digestion, so I'm going to read it out loud. If A is a regular language, and remember what this hypothesis means. This hypothesis means that the language here is tied to a DFA. So there is a DFA-M with this M recognizing L. So we've got this machine out there that tells us everything there is to know, and I should say A instead of L there. Everything there is to know about our language, A. And if there is such a machine, then what we know is that there's this finite bound on how much that machine can distinguish between or remember. So there's this number P, and when you see P, what you really want to think about is it's associated to, it's not exactly equal to, but it's associated with the number of states in the machine. So there's this number P, so that if S is a string that's in A, so it's going to be accepted by our machine M, and it's long, so the computation path of the machine is long, and the computation path visits state in the machine as it bounces along, reading the symbols of S one at a time, then if that sequence of states is long enough, pigeonhole principle tells us we have to visit a state more than once. And what we saw about DFA is that if we visit a state more than once, then we forget about stuff. We can't distinguish between the first time we visited the state and the next time and the next time after that. So that means that we can write our string into pieces. The piece before we got into this repeated state, the piece that tracks our progress until we come back to that state, and then the piece that brings us from that state to an accept state in the machine. And we know that we'll be getting to an accept state in the machine because we've started with a string that's in the language A. And so if we were to pump that middle part that tracks our progress from the state all the way back to the state, and we do that part as many times as we like, we'll still have the machine, when it's computing on any variance of this string, any of these infinitely many different strings, the computation will start at the start state, follow the part that brings us to the base of the cycle, do the cycle sometimes, and then go to an accept state. So each of this infinite family of strings is going to be in the language. So the idea here is that we're identifying some nice feature, some predictability, languages that are recognized by automata. Okay? The goal will be that if we have a language that we can show doesn't have a pumping length, then there's no way that it's going to be recognized by a machine. Okay? Because all regular languages have pumping lengths. There is a number p that tells us that sufficiently long strings in the language bring with them an infinite collection of friends to the language. Yeah, how do you know how to split the string up? That's a great question. So here's a visual that might help with that. So if A is recognized by a DFA-M, and we've got some state diagram that I've abstracted away all the nodes and details. But the idea is that if we know that the computation of the machine M on the string S takes us from the start state to an accept state, and S is large enough, then there will be some repeated state in the computation, and that's what tells us how to split up the string. Because at that repeated state, we can look at the label of the prefix of S that brought us there, and then the label of the substring in S that labels the next time we come back to that state. And then we look at the suffix that brings us home, goes to the accept state. So the machine will go to the accept state when reading it. So the idea here is really if one long string is accepted, that's our string S, then many other similar strings will be accepted too. So if we think of pumping down, we'll get the different string, maybe we can call it S sub 0, which is XZ, without any occurrence of Y, where we don't follow the cycle at all. Or we can pump up and say, hey, I want to do this cycle twice. So we could have X, Y, Y, Z. Or I can go through the cycle another time, X, Y, 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 Z. And we get this infinite collection of strings that are all in our language.